Welcome. We are looking at modeling precipitate growth kinetics in a system in which the diffusivity is a constant. So, we have come up with a free energy functional which will serve our purpose, which will have this property that the second derivative of the free energy with respect to composition will be a constant. Hence, the diffusivity will not be a function of composition. Okay, so we have managed to write such a free energy. So the free energy functional that we wrote is like this: f of c comma eta plus kappa c del c squared plus kappa eta kappa phi del phi squared over the volume. So this is what we are looking at. And f of c comma eta is written as ac squared into 1 minus w of phi plus b 1 minus c whole squared w of phi plus p phi squared into 1 minus phi whole squared with w of phi. I should use same symbol. W of phi is defined as 0 or 1 depending on if phi is less than 0, if phi is greater than 1, and it has the functional form phi cube into 10 minus 15 phi plus 6 phi squared if 0 less than or equal to phi less than or equal to 1. So in the middle range it is going to have this kind of behavior. Okay, so that is the function, that is what is going here. So what is the evolution equation? So we need to define. So the Cahn-Hilliard equation of course is going to be m del squared acting on the del f by nv by del c. So this is the Cahn-Hilliard equation, and the Allen-Cahn equation is going to be dou phi by dou t is equal to minus L and then acting on del f by nv by del phi. So this is going to be the Allen-Cahn equation. So we want to solve them both. Of course, what is del f by nv by del c? So let us also write it down. So del f by nv by del c is nothing but dou f of c comma phi divided by dou c minus 2 kappa c del squared c, and similarly del f by nv by del phi is nothing but dou f of c comma phi divided by dou phi minus 2 kappa phi del square. Okay, so we need to calculate these two quantities. So let me call this as I think I am calling it as h of c and h of phi, because these are the nonlinear functions that we define. Let me see what I call them. Yeah, so let's call this as h of c. H of c is nothing but dou f c comma phi by dou c, which will be nothing but 2ac into 1 minus w of phi minus b into 1 minus c. So 2b into 1 minus c w of phi, and the next term, which is p phi squared into 1 minus phi whole squared, that does not have any c term. So this is the only the coupled part. Similarly, we have to define h of phi, which is dou f of c comma phi divided by dou phi. So now that has a c squared, then a minus sign w prime phi, okay, plus b 1 minus c whole squared w prime of phi plus 2 p phi 1 minus phi 1 minus 2 phi. Okay. Now what is this W prime of phi? So that also needs to be defined, because remember the W of phi itself is defined in 3 parts. So of course the W prime of phi is also defined in 3 parts, is equal to 0 if phi is less than 0, because it continuously remains 0, so the derivative is going to be 0, is 0 if phi is greater than 1, because remember the function is something like this. So the derivative here and the derivative here are going to be 0, because with phi it is not changing. So in between of course it will have 2 parts, so it will have 3 phi squared multiplying 10 minus 15 phi plus 6 phi squared plus phi cube multiplying 12 phi minus 15, right, because we first differentiate this part, keep this the same and keep that the same and differentiate this part, so it is 12 phi minus 15. So that is what the W prime is going to be. So we know h of c, h of phi, so we have dou c by dou t is equal to m and del squared acting on h c of phi comma c minus 2 kappa del squared c, kappa c del squared c. So this is the Hilliard equation, dou phi by dou t equal to minus L h phi of c comma phi minus 2 kappa phi del squared phi. So this is the Alencon equation, and both of these we are now going to use semi implicit Fourier spectral technique to solve. So we need to calculate these quantities using the real space phi and c values. We have to take it to the reciprocal space, then del squared will be replaced by minus ik squared and del squared will be just replaced by k power 4, and similarly here. So this is what is done in the code. So I have written the code, it's a lengthy code, so I don't want to write it here. So I have written the code, I am going to show you the code, and the code also takes about a couple of minutes to run. So I am also going to start the code. So I will start Octave, I will run the code. Okay, so it's called precipitate growth.oct. So that is the code that I am going to run. Okay, so as it is running, let us go take a look at what the code is doing. Okay, so that's what we want to look at. Okay, so what does the code contain? The first we clear all the variables from the memory, and then I define the function. This is the Wang function, and then I define the derivative of Wang function with respect to phi. So this is called f and this is called f prime, so that is why it is fp. So as you can see, it is x cube 10 minus 15x plus 6x squared, and this is 3x squared into 10 minus 15x plus 6x squared plus x cube into 12x minus 15. So that those are the functions. So I have defined the Wang function and Wang function prime. Okay, now I take a 64 by 64 system. I am going to make the code simpler by taking the same number of grid points and same delta x and delta y, everything is going to be the same. Okay, so n is 64 by 64. So I am not distinguishing between nx and ny because I am going to take them to be equal, just to make the code a little bit simpler. So half n is n by 2. So I am going to take a circular precipitate of size 10. Okay, so this is what we did last time. So you take for I equal to 1 to n, j equal to 1 to n, I minus half n squared plus j minus half n squared. If it is less than r squared, you take c to be 1, and in this case we also take phi to be 1, and else we take c to be 0.02. So that is the far field composition, that is the supersaturation in which this precipitate is growing, and phi to be 0. Okay, so this is the end loop. So we have the initial profile. So we take the central line across which we plot the C and we plot the P profile, C profile in red, and the phi profile in B, and we write the solution to a file. This print minus djpg initial profile dot jpg is going to actually print a JPEG file which will have the initial profile. Okay. Now we define del k, of course, we define delta t, we define a, b, p, m, kappa c, kappa phi, everything. They are all one, we always deal with non-dimensional values, and m and n are for the time loop, I and j are for the position loop for c and phi. So first I have to calculate w by calling the function, and if phi happens to be less than 0 or greater than 1, then I am going to make that w 0 or 1 correspondingly. Then I define h of c, which is 2ac into 1 minus w minus 2b into 1 minus c into w, right, because it has only 2 terms. So that is how h of c is calculated. For calculating h of phi, I need Wang prime. So that is what is calculated, and Wang prime should become 1 if phi is less than 0 or greater than 1, else it is the function. So it is ac squared minus ac squared Wang prime plus 2b into 1 minus c whole squared Wang prime plus 2p into phi into 1 minus phi into 1 minus 2 phi. So this is what the h of phi is. So this function is done. So you can see why this calculation takes time. It takes about 2 minutes on my computer to compute this 64 by 64, because there are lots of conditions and lots of calculations, and instead of one Fourier transform there are 2 forward Fourier transforms, 2 inverse Fourier transforms. So it's a little bit computationally intensive. So now I have h c, I have taken the Fourier transform of that. I have h phi, I have taken Fourier transform of that. So h c hat and h phi hat are there, and then we take the Fourier transform of c and phi itself, and then we evolve. So evolving is by first taking the periodic boundary condition, calculating k squared k power 4 using those vectors, and then we evolve c according to the Korn-Hilliard equation, phi according to Allen-Korn equation. So that difference is seen. Here there is k squared, here there is no k squared, here in the denominator there is k power 4, here there is only k squared. So that is because this is Allen-Korn equation and this is Korn-Hilliard equation. So then we complete for all c and phi, then we take it back to real space, we go back, do the c h phi calculation and proceed like this. So after you complete n number of time steps, of course you come back and plot. Okay. So that is what is done here. So finally we plot the function. Except that hold on is still on, so probably everything will be plotted on the same file. So let us take a look at it. Okay, so here you can see, so this box is the initial phi profile, and this is what the final phi profile looks like, and the same box is the initial C profile, except that the far-field composition is slightly different, and you can see that composition now evolves into this profile. The profile is not setting up a proper growth profile, and that is because the far-field composition I have given is very small, and because of periodic boundary conditions the composition is already seeing the other precipitate. Okay, so it is going to go into a regime where the diffusion fields are overlapping. But on a computer like this using Octave, it is difficult to do larger calculation, but of course if you take the far-field composition to be higher and then the system size to be larger, you can do. What is unmistakable is that the composition which was 1 has gone above 1. This is due to the Gibbs-Thompson, and the amount it has gone above 1 is very high, it is about 0.15. That is because the interfacial energy in this system, which has both contributions from phi and c, is really high. But on the other hand, the phi profile always remains at 0 and 1. Composition depending on the size will change, and this increase, and here also it is trying to increase to the same amount, right. So because of the Gibbs-Thompson effect. So this is a model. So using this, if you can do a larger system calculation, then you can look at the growth rate as a function of supersaturation, and you can compare it with the analytical solution. So we will do it as a tutorial. We will look at Frank-Zener analytical solution, how to calculate it for 1D and 2D, and we will then go back to this code, do 1D simulation or pseudo 1D simulation by taking 2D but putting a planar interface where there is no interfacial energy or capillary effect, and look at how the profile looks like. And in the same way we go do the 2D simulation, look at the growth rates and compare and find out what is the effect of Gibbs-Thompson on the growth rate. So that is what we will do as part of a tutorial, but the main purpose behind today's lecture or this lecture is to show that it is possible to combine more than one order parameter, and those order parameters could be conserved and non-conserved. You can have more than one conserved order parameter, you can have more than one non-conserved order parameter. Grain growth is a case where we take more than one non-conserved order parameter, and a scenario like ternary spinodal, for example, is a case where we take more than one conserved order parameter. Okay. Now here is a case where we have taken one conserved and one non-conserved, and very simple equation, so it is Kahn-Hilliard and Allen-Kahn. All the physics is incorporated in the free energy, specifically in the coupled part of the bulk free energy density FFC, phi. So if we get that right, then we can get all the physics right, and we can write the evolution equation, and using the evolution equation then we can also see how the system evolves. Okay, so it is possible using such a model to compare some of the analytical results of Frank and Zener and how they compare with the numerical results that we have in this case. So I will also give a reference to this paper. From the paper you can see that the model results agree well with the analytical results in the case of 1D, and in the case of 2D there is deviation which can be attributed to the Gibbs-Thompson effect. So it is possible to do computer experiment to find out the effect of Gibbs-Thompson effect, for example on growth rates and things like that. But in this case we have used the two order parameter system as just a model system to get the particular assumption we want, namely that diffusivity remains a constant. But there are other cases where we have to use multiple order parameters because the physics demands so, and there could be cases where both are there. So you will have more than one order parameter, some of them for physical reasons, some of them to implement the particular scenario that you want to implement in the phase field model. So we will see a few more examples of this type, more than one order parameter, and what type of microstructural evolution they lead to in the remaining part of this course. Thank you.